Okay. Does anybody know anything about the United States education system at all? And like that there's actually fixed metrics that you're supposed to learn at the end of middle school and at the end of high school? Okay. Okay. Did we talk about how much the United States education system costs last time? Okay. So it is not a money thing. You actually pay more for your middle school and high school education than you did for your college education. A lot more. If you're going here, this is actually quite reasonable compared to that. So, so one of the things you're actually supposed to learn in a middle school education is actually conversions. So at the end of middle school, you're actually supposed to be able to do all the conversions that you'd be able to do for doing metric to feet, pounds, the U.S. system. Okay. And that one is actually by international treaty. We actually made an international treaty. It was supposed to be in completion by 1986-ish. It got moved a few times, so 1990, let's say. And everybody in the United States was supposed to be able to do metric and US and do those conversions. we're not exactly doing a great job on that one, right? But funny enough, do you guys know the only nation to actually uphold the Paris Accord, to actually meet our goals for the Paris Climate Accord? The United States of America. We're the only one that actually met it. Japan is the only country that actually did what they said they were going to do, but they did not meet the accord, their goal at the end of it. They fell just a little short. So kudos to Japan, because they actually are the ones that like worked hard on it. The U.S. purely by accident met our goals because we figured out how to go to natural gas and figure out how to make that cheaper. So purely by accident, but we did it. Everybody else missed their goals by a long shot. So just as a funny, like, hey, sir, this is just an amusing thing. Now let's talk about elements, compounds, and the periodic table. Now you will always have access to the periodic table on every exam. Okay. That will never count towards your 2-page front and back, 1-page front and back of notes. So please don't get concerned about that. I actually had somebody ask me about that. I was very concerned, which fair. Now, a pure substance will contain 2 or more chemically combined elements. This can be a compound. Compounds will combine elements in specific ratios. I already did this, didn't I? Yeah. Okay, so let me ask you a little question. All right, so CO2, carbon dioxide, okay? Is that different when a person breathes it out, when it comes out of the tail engine of a car, and when it comes out of a plant? Does that act differently? Okay, according to Greenpeace, does anybody know what Greenpeace is? Okay, they are a tens of... Mm-hmm. Okay, so the PowerPoint is actually several locations, but probably the easiest one is to go to the Canvas course, home, midway through the page, there's a link to the PowerPoints. Okay, got it? Okay. Now, Greenpeace is an organization that's funded somewhere between $10 and $20 billion a year. They're one of the single largest green groups on the planet. Very, very powerful, very influential. For about 20 years, they had on their website that the CO2 that comes out of an animal and CO2 that comes out of the green, like a tree from the Amazon, is beneficial to the world. The CO2 that comes out of a human or a car is somehow harming the world, comparison-wise. Which they're all the exact same. No, they have no idea what they're talking about. And I had a poor student used Greenpeace as a reference on a presentation on environmental chemistry, and oh my god, So just to be clear, if you ever see something like that, carbon dioxide, that ratio always means it's the exact same thing chemically, right? It's the same no matter what. Okay? It doesn't matter where it comes from. Chemically, it's the same. It's going to do the same chemistry. They're equally harmful or helpful. Okay? CO2 is kind of a weird one. And we'll just say for now, it is both harmful and helpful. It entirely depends on the situations. Okay? So
stick your head in the bag and breathe it, but choose neither.
Exactly. It entirely depends on the situation you're looking at and how much in that situation, right? Yeah. So, chemical formulas. These are going to show that, for example, table salt is composed of 1 sodium and 1 chlorine, right? H2O2, that's hydrogen peroxide. H2O2 is always going to be hydrogen peroxide, right? Okay. So, a chemical formula which identifies which elements and how many atoms of each element is present in a compound. And so this is always going to tell you that information. Now, keep in mind that if you change these numbers, you are going to change that identity, right? And so you have to be really careful, okay? There's a bit more layers and nuance that we're going to discuss as we go along here, but this is a good entry point. So, how does matter change? So we have physical changes. It's going to be a change in the state of matter. It's going to represent the physical change. For example, going from ice to liquid or liquid to frozen solid. Okay? That's going to be a physical change. The form of the matter has changed, but your identity will remain the same. You still have water either way, right? If we were to evaporate that water, it's still water, isn't it? Okay? If we were to take that water and split into pieces, still water, right? So as long as it's still water at the end of that change, it's going to be a physical change. Okay. Now let's talk about chemical changes. There's going to be changes that result in the change of the chemical identity of the substance. So the stereotypical chemical change is going to be burning. Now there's a kind of easy way to remember these because they're typically referred to as chemical reactions. So if you go, hey, that's a reaction. Well, that's actually a chemical change, isn't it? Okay. And you pretty much instinctively know these because you end up with something completely different at the end, right? Yeah. So, for example, burning coal, you don't end up with coal at the end, do you? You might end up with a little bit of soup. You're going to end up with gas, which is CO2, and water. Okay. If it's hot enough, and everything's pure enough, you'll just end up with the CO2 and water, by the way, in case you're wondering. Anybody have any questions about that? Okay, so remember, you're going to fundamentally change the identity, that chemical, okay? All right, so this is a chemical equation. I want to point out that it is absolutely an equation, okay? It is variables. We're using these variables to represent chemical identities. And those variables are those symbols on the periodic table. And so those are things like carbon, oxygen, or O2 in this case. Then we have this arrow here. This arrow is just an equal sign that has direction to it. Okay? It's just an equal sign that says, hey, we're talking about this going from this to this, okay? But everything on both sides of this has to be equal, doesn't it? Okay? You have to have the same number of carbons. You have to have the same number of oxygens. You have to have the same overall mass. Okay? Because they're equal. This right here, any conditions above the reaction arrow, those are conditions you need for this reaction to occur. Okay? For example, this one right here actually needs heat to start this reaction. That's why if you just sit coal there, it can just sit there for a long, long time, right? That reaction will go very, very slow. And eventually it will tar up, but it goes really slow. Okay? And it's why your car doesn't spontaneously burst into flames right now. unless you have an EV in which is a slightly different reaction, but also could burst into flames right now. Actually, more likely to burst into flames right now, which is something. So CO2 is the final product here. And again, you'll notice you have a same number of carbons and oxygens, right? But now they're rearranged. And so that's carbon dioxide gas. Okay. This, on the other hand, was coal reacting with the oxygen in the air. That's that equation for burning that coal, isn't it? Okay. Note again that these are actually variables. You know how you would have like taken a math class and they would go X, Y, Z. If they were really amazing math teachers, maybe they throw in an A, B, C while they're at it. These are just variables, okay? And they literally just stand for, it's that thing on the periodic table, okay? So you could have actually had chemistry where they had literally just put the atomic numbers instead. That could have developed and came into existence. They didn't do it because people got confused. But they liked the fancy names better. But honestly, you very well could have, okay? And every single thing on that periodic table is true within this, right? So the periodic table masses, the periodic table atomic numbers are true. All those things are true, okay? It's carrying everything from that periodic table into this equation. It's just representing it with C. Okay. What does that stand for, by the way? Solid. You got it. Perfect. Perfect. You'll see I do this a lot. And one of the reasons I do this is I want you to actually try to think forward. Most of this stuff you can come up with on your own. You don't actually need me to tell you. I mean, like, what's that? Either one, but you answered last time. So. Oh, yeah. Yeah, gas. You got it. Yeah, so that's gas, right? And if you had an L there, that would be? Liquid. If you had an AQ, what would that be? Dissolved in water or aqueous, yeah. Yeah, like aqua, right? So aqua, aqueous. And so, like, you don't really need to know everything to answer questions. You kind of just need enough to interact and then reason through. Okay? So, this side, the left side, is always what's called reactants. They're the stuff you put together for a reaction. The right side is always the products. It's the stuff you get out of the reaction, i.e. produce, right? And then the middle arrow, that's always the reaction arrow. It shows you which direction you're going, okay? So we're going from reactants to products, right?
Can they always produce heat?
No.
Sometimes they emit light.
They can emit light. They can actually suck heat up.
Okay.
That's how cooling packs work.
Okay.
You know how like you break the thing and it.
Mm-hmm.
Yep. That's how that works.
So that was just an example of heat there for
that
the
is
reaction arrow.
because that's that one right there.
Okay.
Yeah. And actually, this one's not saying that produces heat right now.
Oh.
It's saying it requires heat to start.
Oh, like a catalyst then.
Exactly.
Okay.
Yeah. And so you actually like have to put a match to the coals, right? For them to start. Once they start, they produce their own heat to make other reactions within that start. And that's why you like pick up coals with tongs and put them different places to go faster, right? Yeah. That's what that's telling you. Neat, huh? You didn't realize that like things that you did in life had like ways of representing them. Already figured out, huh? Okay. Anybody have any questions about that so far? All right. So let's talk about balancing these chemical equations. First off, man, I need more of those O2s. Let's say I had two of these somehow, and I need four oxygens. Can I just put a 4 down here? No, I can't put a 4 down there, right? That would be an entirely different chemical, right? If I had wanted 2 carbons and 4 oxygens here, C2O4, would that be carbon dioxide anymore? No, it'd be an entirely different chemical, right? Okay. Okay, that would be that'd be a lot more harmful to the environment, by the way. That chemical would actually like destroy the planet if that's what was produced by every time we burn something. That one would be bad. We'd be Venus right now. Because that would literally be an acid in the air, absorbing almost all of the infrared. It'd be brutal. So obviously that's not what's produced, right? And so you gotta be really careful. These numbers that you would put in front of here, these are called coefficients. You'll notice it's the exact same word for math because it is the same thing. Okay. Yeah. And so what we do is we'd put like a 2 here, 2 here, and that would give you larger numbers, right? And so we just multiply the entire things. Okay. Okay. Now, whenever you balance chemical equations, they always have to be balanced on both sides. And this is because the law of conservation of mass. And so what that says is the matter only changes form. So the amount of matter on the reactant side and the product side have to be equal. And remember that having a carbon and 2 oxygens, that is a mass, isn't it? You can actually see those masses up on the periodic tables, can't you? Yeah. And so you have the same overall mass on each side of a reaction, always. Now, notice I said overall mass. The mass of this carbon, is it going to be the same as that over here? I got a little more specific, didn't I? Okay, so the mass of the carbon here plus the oxygen is the same as the carbon and oxygen on this side, right? The mass of the carbon over here is not the same as all the products, is it? Can't be, because you're actually adding other stuff to it, aren't you? Okay? And so be very careful about that. You're going to be tempted to try to do that, where I'll give you like 2 grams of carbon. How many grams of CO2 did you make? Well, it's not 2 grams. Okay, it's tempting because man, that would make problems easy, wouldn't it? But it's absolutely not. Okay. Now, if I gave you 4 grams of CO2 are produced, how many grams of reactants did you have? Well, 4 grams, right? Because I have 4 grams on this side, it has to be 4 grams over here, doesn't it? Okay. Okay. So again, whenever you're balancing these chemical equations, you have to insert these coefficients. So what you're going to do to balance a chemical equation is you're going to examine the original equation. You're going to ask, is it balanced? Do I have the same number of carbons, the same number of oxygens, same number of hydrogens? Okay. And if you have the same numbers on both sides, congratulations, you're done. Great. Right. And keep that in mind from now on. That's always the win condition. Right. If you have the same numbers on both sides, you got it. You're done. So the next step is you're going to balance that equation one element at a time by adding coefficients. Now, yes, you're balancing one atom at a time. I'm looking, do I have the same number of carbons on both sides? Same number of oxygens on both sides? But if I'm adding coefficients in front of here, I'm not just changing carbon, right? I'm changing both of these things, okay? So this is one of those, that's why I kept stressing you can't just like write in 2 here and just, yeah, because people get confused here and causes them issues for weeks. And finally they're like, oh my goodness. Okay. So once you've put in a coefficient, you're going to double check, hey, did that balance my number of carbons? Did that balance my number of oxygens? Okay. And then if it did, congratulations, you're almost done. If it didn't, you're going to have to add coefficients in other places to try to balance that. Now, I'm going to point out something that's going to complicate this a little bit, but will really help you out, is always start at the most complex thing, okay? Because it's the thing that's the most difficult to balance. Once you get it done, everything else falls in line, okay? So for example, this would be the one you want to balance first, with this being the thing you want to balance it against. And the reason you want to do it is because this is just one carbon. I can put any number in front of there, right? So once I have this done, I just throw whatever number I want in front of there and I'm good. Okay? And so always start off on the hardest stuff first. If you try to do the easy stuff first, you're just going to redo it over and over and over. Okay? Okay. Now, the last thing you always need to do in any balanced reaction, okay, is you need to divide it by any number that everything's divisible by. Okay? You need to reduce those coefficients to the lowest whole numbers possible. All right? So this is why this is 1, 1, 1 for the coefficients here. Is because, yeah, we could have put 4, 4, 4, right? And it would be balanced. But the last rule, we got to divide by 4, don't we? Because they're all divisible by 4. Okay. And that's just a, hey, this makes no sense to multiply everything by a large number, right? Yeah. That just makes it more complicated to look at. All right. Does everybody kind of have an idea of that? This is a very much a practice thing, okay? So practice this on the homeworks. And if you need any help, please come in and talk. Okay? Come in to me, come into the tutors, whichever way. All the tutors and me all know how to balance equations. And it really, really, really is just like a practice thing. Once you've done it a few times, all of them are going to get pretty easy. Okay? Kind of like when you start riding a bike, right? Okay. So let's talk a bit about math. System International de Units is the modern day version of our metric system. Now, what happened is actually in France, they used to have different units and different names for things, basically across the river, across the street. You could go to like 3 different universities on the same street, and they would have completely different names for compounds and completely different units, and nobody could agree on anything. And so it got to be such a mess that they got together and hashed out a system. Now, having said this, this was a very political process. This board of people have gotten into some truly amazing fights over the years. One time they stopped meeting for about 10 years, and they didn't actually start meeting again until one of them died. So, and sometimes they make decisions that are really strange, but at least we have some sort of unity, right? We can discuss things. So the standard unit of mass is going to be the kilogram. That is the only standard unit of mass in the SI system that has a prefix, which is the kilo here. Okay. We'll talk about prefixes in just a second. The standard unit for volume is the liter. The standard unit for length is the meter. And everybody's probably heard of those before. If not, uses them. So the prefixes, these can be applied to metric system units. These change the meaning of the unit by powers of 10. Actually, prefixes can be applied to anything. You could do a kilo inch. Nobody would know what you're talking about because people don't do it. But you can. I mean, you can use them for anything. You could do a kilo dollar. Technically, people do kilo dollars. If I say I get paid 10K, then that means 10 kilo dollars, right? $10,000, yeah. Now, I'm going to say something that's really ridiculous and funny. There is no branch of science that's actually perfect about using the SI units and prefixes correctly. Environmental sciences are really bad about it, actually. Really bad, which is funny because they're the newest branch. So they have no excuse. There's no historical anything to stop them. They just or sometimes purposefully obfuscating things. So no reason not to, and they did it. But sciences are actually probably notoriously bad about it. Industry is notoriously bad. Governments are some of the worst about it. And the funny enough, the people who are probably the best about using SI units are drug dealers. You notice that they use SI units for everything. You buy drugs, they're going to be in liters or kilograms, which is just, you get busted for drugs. They're in liters or kilograms, and they're always right. Which, I don't know what happened there. I guess they have to follow some rules somewhere, right? And those were the ones they said, this is the limit. Anyways, giga. You guys have all probably heard of these prefixes before. Another group that's pretty good about prefixes use is actually computer science. Okay, so your computers have trained you in prefixes up to now. You may not have paid attention, but they did. So giga, like a gigabyte, right? Or if your internet connection, gigabit, right? And that's going to be 1 billion bytes. So what they were telling you is your internet connection has half a gigabit or a gigabit. It had 1 billion bits. Okay. Mega. These are like my PowerPoints. I'm super inefficient on my PowerPoints, by the way. Like the size of a video, aren't they? And those are in megabytes. And so you'd put a big M in front of the byte, right? Okay. If I had $1 megadollar, I'd be pretty happy, wouldn't I? That's $1 million. Kilo. This is actually one of the few ones that has a lowercase. So keep that in mind. This is actually a lowercase k. The uppercase k is a whole different thing. Okay. And so you put a lowercase k in front of your unit. For example, there's the kilogram. Everybody knows kilogram, right? Okay. Again, those damn drug dealers are really good about this, aren't they? Give me a kilo. You know exactly what they're talking about here. Kilogram. Nobody else is quite that great about it, but they are. 1,000, of course, everybody knows kilo because you've heard it everywhere around you, right? For all sorts of reasons. You have the base unit. This would actually be 10 to the 0 in case you're wondering, which is 1. So the base unit is just itself, right? This would be things like grams, liters, meters, etc. Here we have deci, which is a small d. That's like decimal, right? And so it's 1/10. Okay? Or divide by 10. Another way of saying divide by 10 is 10 to the negative 1. Okay.
No Sharpies for you.
Thank you so much. Sorry, like depending on you for my markers. Thank you so much. I'll have to remember to bring some. It's not expecting that. This one got cleared out. Okay, so what do you notice about these three things? They're the same. Yeah. They're the exact same. Okay. So all three of those numbers are the exact same number, aren't they? All right. So keep that in mind whenever you're doing these things. 10 to the 0 equals 1. Okay. 10 to the first equals what? 10. You got it. Okay. Okay. Does it equal this? Very careful about that. Does anybody know what happens when you do that? So you multiply 10 to the second times 10 to the negative 1. So the easy way to do this, you just add these together. Okay. So if you multiply here, you add those. If you divide, that would be a subtraction. Okay. And so 2 minus 1, 10 to the first, right? Okay. Yeah, so I often find people do not actually like know that math. It's become something that's doesn't always get communicated. So I want to double check because it's somewhere where people oftentimes fall into a hole and have difficulties. So deci, decimal, 1/10. Centi, like century, right? Same sort of root word. This is 1/100th, so centimeter. 1/100th of a meter, right? Or another way of saying that is there's 100 centimeters is a meter, right? Okay. This would be milli. And so, like milliliter, you may have heard of. And so that'd be 1,000th of a liter or 1,000 milliliters in a liter. Micro, this right here is not actually a U, but most people will put U's. And that's actually called a mu. It's a Greek letter. Okay. Be very, very, very careful if any of you are planning on being nurses or on going into the medical field. This right here oftentimes gets written in such a way that looks like an M. Okay. And so what you'll oftentimes see is that doctor's note will say something like loose cursive looking M, liter of morphine.
Oh.
And then the nurse will try to give that person 1,000 microliters of morphine drip. There is actually. You put MC. But again, even like, unfortunately, this is just one of those things that, like, the mu shouldn't be something you can just put a U. It's fine if you put a U. It really should not be an issue, but people are sloppy, and when they get tired, they get sloppier, right? And then, so we teach everybody the prefixes so that they know the prefixes, and they go, like, this is one of those things I actually get approached a couple times each year by former students that are now nurses, and are like, you know what, Dr. Clausen, those prefixes, I know I was like, I hate this and didn't want to do it, but you're right. Somebody tried to give somebody 1,000 times the dose of morphine and kill them. My training nurse usually, but yeah. So it's just something I get approached by all the time, and I always just point it out because you're probably going to see it at some point. If you're going in the med field, somebody's going to try to give somebody the wrong dose. If you're unsure ever, especially here, this is one of the big ones that happens a lot. Just go and ask the doctor and say, did you mean this? And then they'll look and go, oh my God, no. Yeah. I actually know somebody that they tried to give the person 1,000 times the dose. I also know another person that they tried to give 1,000,000 times the dose. The machine wouldn't do it. So, thank God. But the machine will do the 1,000 times the dose. So I don't know if maybe they have newer machines that start flagging that, but God, I hope they do. But and that happens way more than you think. Like, truly. And that's on the ones where you can dial it up on the machine. There are times you have to actually measure these doses out. So keep that in mind, that these prefixes are actually like an actual life-saving thing. So, and if you know the prefixes, you can watch the nurse put in your units and go, oh, no. That's that one actually was my advisor. He was getting morphine and they tried to dial it up, and he looks over at the notes and goes, no, you don't put that in. And the nurse started arguing with him. And he said, no, you go talk to the damn doctor. I refuse treatment until then. And he saved his own life. So, yeah, that happens like pretty regularly. It's not uncommon at all. Anyways, MC is the other way you can do micro. By the way, micro you may recognize from microbiology, and that's because everything there you're looking at is in the size of micrometers. Okay, and so it's 1,000,000th of a meter, or there's 1 million micrometers in a meter, or for another example, there's 1 million microliters is 1 liter. Okay. Nano. You guys may have heard of nano before. Has anybody ever heard of that in any way? Yeah, like nanobytes, nanobots. Yeah, exactly. Or nanoprocessor. Yeah. So that's this one. So it's a billionth of a byte. Nanoprocessors are measured in nanometers. And that's how small the circuitry on them is. Though that has broken down recently. So the 2nm process is not 2 nanometers. Anyways, it's 1 billionth of a meter, 1 billionth of a liter, whichever we want to talk about. If they gave me a nano dollar, I'd be very disappointed. Yeah. Okay. Now, equivalents. Equivalent units are literally what I was doing up there, right? They're just the same thing written out. Okay. So what you're really just saying is 1 deciliter is equal to the exact same thing, right? 0.1 liter. Those are just the exact same thing. One has the prefix here representing it. Can everybody understand that okay? And so they are equivalent, right? Now, equivalencies can always be represented as what's called conversion factors. It's where you've divided one side over into the other, okay? And that means that 10 deciliters, for example, over 1 liter would equal 1, isn't it? Because it's the same thing divided by the same thing, isn't it? Okay? This right here would be the other way for the conversion factor. Notice we just flipped it. We've divided the other side over. And so again, that would actually just equal 1, wouldn't it? Now, these are very convenient because whenever you're doing math, you can always multiply anything by 1, can't you? And so when you're doing math and trying to convert units, you can take these conversion factors, which are the same thing on both sides of them, right? And you can always just multiply anything you want by them. And that way you can work yourself through the units and convert units. Okay? Very, very useful skill, by the way. You're all going to not believe me. But like I've ordered pallets of solar panels from China, went through all of the tariffs and all that stuff. And I don't know anything about any of that. But I know unit conversions. I used it hundreds of times on that and did it. And once you know unit conversions, it's not so hard. Okay? And people don't know this, but like most businesses want Excel, but what they really mean is they want you to be able to use unit conversions over and over and over really quick. Okay? That's actually what they're asking, right? You'd be shocked about the number of jobs this actually is. Okay, so conversion factors allow you to go from one quantity to another using these equivalent units. Okay. So this is the overall how do you do a math problem here for dimensional analysis. So converting units to equivalent units is typically referred to as dimensional analysis, but can just be referred to as conversion sometimes. The number 1 step is you determine the units on your final answer. Did I already talk about how you can solve any problem in your life, no matter how big? No? Okay. Sorry, so I have 2 sections of this class, but one section started a week ago at Green Hills High School. And so until we catch up to each other, I'm going to be like, which one did I do that in? Once we catch up to each other, we'll mostly follow each other nicely. So I won't have so many troubles. So every problem in your life can actually be incremented towards being solved by a pretty simple formula, okay? And this really is true. It's like life advice that I'm couching in science and math advice, okay? But I'm going to be concentrating on the science and math part of this. Sorry. All right. So every problem, if you want to try to solve it, there's a 3-step procedure, okay? What do I have? What do I need? How do I get there? Everybody got that? Everybody with me? Can we say it with me? What do I have? What do I need? How do I get there? Okay? And so you cite what you have. And we'll do concrete examples in just a bit. What units do I currently have? What have I been given? And you put that all together so you can see it easily, okay? And then you state, what do I need? What units do I want to be in? What do I want to get at the end of this problem, okay? But notice, really, it's your life, too, that works. What do I have now to work with, right? Where do I want to be in a year? Okay? And then you chart how to get there, okay? And we have a very formal way of doing that we're going to have the given unit that we started with. And then we're going to put a unit that moves us towards what we desire to be at the end, right? And that's going to go on top because that's what we want to be at. Okay. And then we write out our units in such a way that they cancel out and give us what we want at the end. And that's the how do we get there, right? Always start with the units first. Don't worry about the numbers until you're ready to do the math. Okay? Because you need the plan first before you can execute, don't you? Okay. I know it's like profound life advice. This sounds super simple, but is actually incredibly profound and useful. And it's trivialized into how do you do math problems. Yeah, that's me. That's my job. Like discuss the profundities of the universe, the secrets, and trivialize them into a simple word problem. Yep. Significant figures. This is going to be measuring matter. It's going to rely on the precision of your instruments that are used to measure it. It's very important to report calculated answers reasonably. If I were to just like measure randomly with this cup here and then report you a unit that this is 1.0001 liters, that sounds really accurate, doesn't it? That doesn't sound like I just randomly poured this cup out once, right? Because I'm kind of lying to you, aren't I? Yeah. I'm using a lot more precision, a lot less uncertainty in my number I'm reporting than actually exists, right? And so you got to be very careful about that. The numbers you get out on your calculator will look like they have a lot of decimal places, but we need to use sig fig, significant figures, to determine what the actual uncertainty is, okay? Now, this is a very entry-level way to do this. If you ever want to go further into sciences, there's actually much better ways of doing this that make more sense, but as a ballpark, it works very well, actually. Okay. All right. So in any measurement, the significant figures are going to be digits that are known with the certainty plus one estimated digit. And that's where your uncertainty is. Okay. That's the I'm not so sure about this number. That's what you're telling people. That last digit, that last decimal place, that's the one you're going, hey, I didn't get that one perfect. I'm not sure exactly how far that one is. Okay. The other ones you know. You got those. Digital devices will automatically actually show us our number of significant figures in the digital readout. So if you use the balances, for example, they're going to show you the number of significant figures right then and there. Okay. And the last digit that you record, that is where your uncertainty is. And you'll actually see that next week when we start messing around with balances and stuff, that it'll actually like bob up and down because you're breathing and stuff. And so you'll go, oh my goodness, this actually really makes sense. That's why we have a lab. It helps you understand. So now, analog devices are different. Does anybody know what I mean when I say analog devices? Yeah, you have to manually figure that out, right? It can be things like a measuring cup, but it also could be like a ruler, right? And those ones, what you do is you go to the lines. Do you mind if I borrow you? Thank you so much. Okay. So what you'll do is, like, let's say this is a ruler. Okay. And so you're measuring and your thing's right here. It's about halfway, let's say. Okay. And so what you'll see is this one, these are certain, aren't they? I know it's more than that 3 right there, right? This is where my uncertainty is, isn't it? Okay? About half is not. And so what I would do is I'd go 3.5. This is where my uncertainty is, right? And that's the one I don't know perfectly. The 3, though, I know. Okay? Is that making some sense? Another great example of that is your bank account, actually. Like, you all probably know your bank account to the hundreds, right? And so if you were to give a number, you would give it with that last digit for your bank account being the one you remember. The rest of the digits you just drop, don't you? Okay? So if you have $151.01, you probably don't remember the cents. You might remember the ones place, right? But not be 100% sure. Okay? And so you'd go 151, right? And if you don't care as much about the ones, maybe you only remember 150. And that's what you give, and that last digit's actually where you're not sure. I could have bought a $2 taco, and now I'm at 149, right? But I'm close to 150. Okay? You're actually applying significant figures. You just didn't know it, right? Because you're representing your uncertainty. Okay, so significant figures, zeros. Zeros are actually the troublemakers. That's where people are going to have issues. And that's because zeros are actually used for two reasons when we write numbers out. Zero is the number, zero, but it's also a placeholder, right? So if I write out 100, can I write 100 without putting those zeros? I can't, can I? No, they're placeholders, right? And so those zeros there, they're not significant right now, okay? That'd be like my bank account. I only know it to the hundreds. I have $100. You know, it could be 140. It could be 70 because it's, something around to it. It could be a lot of things, right? But somewhere around 100, okay? If I was to write this, on the other hand, that's a period, by the way. I have a tablet that's coming, but I guess I missed it. Can you guys see the period okay? Okay. So 100 period, right? Decimal place. That actually means I have 100, okay? So I could have 99.9. I could have 100.2. But they round to 100, okay? I know it to that place. That's where my error starts in, okay? Okay, now, the significant zeros are going to be zeros that are not just because of their position in the number, okay? They're actually expressly there for a reason. So, for example, a zero in a number without a decimal point to be significant has to be shown by putting a decimal point after that zero for that zero to be significant, and these ones that would be before the decimal place. Okay? Without the decimal place, these, for example, are not significant. Okay? They're placeholders. Now, to indicate significant zeros in large numbers, we draw a line above the significant zero. So if I had wanted to make those significant, I could have also done that. Drawn a line to represent those are significant. Okay? Okay. If I wanted to make only the tens place significant, line there. Okay. Exact numbers are going to be important as well. So an exact number is going to be something that definitionally has to be true. So those prefixes, you may notice that I didn't define significant figures in those prefixes here because these are exact numbers. By definition, they're always true. Okay? These things never have any significant figures at all, or another way of saying it is they have infinite significant figures. Okay? Because definitionally they're true. Right? Another example of an exact number is number of people. If we sit here counting up the number of people and we can exactly count them, I can't have a 0.1 person, right? So that's an exact number. Okay. If we count so many people that we can no longer figure out for sure if we're correct, and so we have uncertainty, that's where we start getting fractional people. So there's 2.1 children per family. Yeah, that's that fractional people, right? Yeah, there is no 2.1 family, right? Okay. Now, these are the examples of different significant figures. For example, this right here, none of them are zeros, so 41 grams here. Notice that you always have to have a number, significant figures, and units, right? Those are the three important things you always have to have on every single number you represent, okay? So we have 4 and 1. So the number of significant figures there is 2. And we just count 1, 2. Okay. You always want to start on the left whenever you're counting sig figs. It just makes your life a lot easier. And so 15.3, that is 1, 2, 3 sig figs. Okay. If you put a 0 between significant figures, that 0 becomes significant. Okay? Because you didn't have to put a 0 there, right? You could have put a 1, 2, whatever. Okay? And so 101, there's 1, 2, 3 sig figs. 6.071, 1, 2, 3, 4 sig figs, right? If we come over here, see you have a decimal place there. Okay. So you start counting at the left if you have a decimal place, and everything from a significant figure on the left on becomes significant. And so this is 1, 2 sig figs. This one right here is 1, 2, 3, 4 sig figs. Even though those zeros at the end, because it has a decimal place, we start counting at the left. This is significant. And so everything after it has to be significant. Okay, let's talk about a 0 that's not significant. So here we have no significant figures until we get here, right? And so those here zeros are placeholders. They're just there to move the decimal place, right? And so we go, nope, nope, 1 sig fig. What would happen if we put a 1 here, by the way? Yeah, it'd be 3 sig figs, right? If we had a 1 here, that would be 2 sig figs, right? Anywhere you have that significant figure, that's where you start counting, right? Okay. And so this one right here, again, another decimal place problem. So again, not. We go on till the 2, don't we? And now finally a significant figure. Okay. And so the 2 and 4, that gives us 2 significant figures. All right. This one right here, it has no decimal places. They're just large numbers, and they don't have any lines above the top. So this one has 1, 2 significant figures. No decimal place, so we don't count the rest of these zeros. Okay. Over here, 1, 2, 3. And now we have zeros for the rest, so we don't count them. And again, no decimal place, right? Okay, let's talk about calculating numbers and rounding. First off, when you're doing your calculations, don't round. Okay? If you can avoid rounding, don't round. Any calculations that you do, if you're still calculating, don't round. Now, if you just cannot type all those digits, it's too long. Figure out your sig figs so far, and then give yourself an extra 2 sig figs that you're going to use for all your calculations. Okay? Because the problem is, if you count your number of sig figs and you just start rounding each step of the way, what's going to happen if I just round up every time? I'm going to get a very different answer, aren't I? Okay? And this is actually has a really interesting real-world example. Anybody ever watched Superman 2 from back in the day? Yeah, good movie, right? Yeah, awesome. So you know the Superman virus in that, and yeah, okay. So it's called the Superman virus now, usually, because it was featured in Superman 2, which is one of the better Superman movies, honestly. And so what it is most recently it was actually used by a Ukrainian hacker group on a relatively large chain of banks on their ATMs. And so it is a virus that takes every time a bank does a calculation, what the bank normally does is they stop at the 3rd decimal place and they round that down and give it to themselves. And so actually the banks are stealing small amounts of money from you. Mostly. But clever hackers can instead insert a program, and essentially the 4th decimal place, they go and round that off and give that to themselves. And, banks calculate transactions millions of times a day, right? So, yeah, 4th decimal place, not a lot of money, right? It's 100th of a penny. But if you do it 1 million times a day, you're racking up a lot of money, aren't you? And so the last time this was done, they stole $400 million in a couple weeks. As far as I know, they actually got away with that, though they may have busted them now. That was like 5 years ago. So I don't know if they actually ever caught those people, to be honest. But it's been done, as far as I know, it's been done 4 to 6 times. So I'm not sure if it was different groups doing it for two of those, so I couldn't tell you.
That's the premise of the entire movie Office Space. Have you seen that movie?
Yes. Yep. Again, they got that from the Superman movie, and the Superman movie got it from a hacker group in the 80s.
Interesting, because that
Not
Office Space was made in 2002, and I was like, I remember a movie about that. So when was the Superman movie made?
I want to say 1980s. Yeah. The first one's like late 70s, right? And then yeah, which it also is quite good. It's long, but it's good. Anyways, yeah, it's been done basically since ATM started being a thing, and the banks started calculating everything out using computers, and they just figure out new ways of inserting the virus and collecting an account, and there you go. And it takes a while to figure it out. Though in the Office Space one, it does not take long to figure out.
It's hilarious.
They mess it up really bad.
Yes.
But that was a good example too. I feel like the Superman movie is more likely to hit people, but still not very likely. So they haven't featured it in a long time. It's a shame. It does. Okay, so let's talk about some rounding rules. So again, you don't round until the end. You figure out your sig figs, and then you round at the very end when you have your answer. Okay? And how you round is when you're adding, subtracting, multiplying, or dividing, you're going to get numbers that may end up having more decimal places than you should have, right? Or maybe even less. Okay, you got to be careful about that. If it has less, you put extra zeros until you get to your sig fig. Okay? Because sometimes things just go into each other and you get one decimal deal, right? But if you have too many decimal places and you need to get rid of those, what you're going to do is you're going to look at the next decimal place down. If it is 4 or lower, you're going to round down. Okay? Now, your book's going to tell you something, but it is actually wrong. Okay? But in this class, it's fine if you use your book's way of doing it. I'm fine. I don't care. Okay? You'll be okay. Your book tells you if it's 5 or greater, you round up. Okay? However, I'm going to tell you that is wrong, and I'm going to tell you the correct way of doing it, because if you actually do that in the real world, you can cause massive damage. Okay? Especially if you're like sitting there doing an order form for a big business, and you have hundreds of times you do that, they're going to compound, and you're going to cheat somebody out of a lot of money. Okay? So how you do this is you are going to, if it is a 5. Now, if you go 1 through 10, 5 is actually the very middle number. Everybody realize that? So it shouldn't round up or down, should it? It should round both ways. Okay? And to cause if you round it up every single time, you're going to end up with large numbers every time, aren't you? Because you're rounding up every single time when you shouldn't be. And so what you need to do is, if you see a 5 for your next number, you actually want to round it up half the time, down half the time. Okay? And the way you do that is you look at this number you're going to be rounding it in. If it's a 4, you round it down. So if it's an even number, you round down. If it's an odd number, on the other hand, you round it up. Okay? And that's how you accomplish rounding it the same, different each time.
So
it should half and half.
You're just asking us to look at the preceding number. So look from 1s to 10s.
Exactly.
If my 10 is a 4, go ahead and
always round it to an even number.
Okay.
Yeah. And that's just a better way of doing it. It will give you a lot less rounding errors in the long run. Now, again, for this course, if you want to round 5 up every time, I'm not going to kill you over it. Whatever. Okay? I know your book tells you that. It is wrong, but there you go. At least you know how to do it properly now. Okay? And there actually is more advanced ways mathematically you can do this, or in computers you can do this. In which case they actually look at they have a little counter basically that you do, and you do it once one way, once the other way. Dun dun dun.
Still be off if they're odd numbers, though.
Huh?
It would still be off if it was an odd number if you were doing 3 calculations.
No, that's a more correct way. But yeah, it would be off if you do odd numbers of calculations, but it's a minimization thing. Yeah. See, you just gotta kind of do your best. Yeah. That's uncertainty for you, right? Okay, so the rules for significant figures and calculations, they are going to be different depending on if it's an addition, subtraction, or a multiplication and division. Okay? So multiplication, division, you're going to give the least number of significant digit for your measure, your final answer. Okay? And the reason you need to do this is, let's give an example after I say the addition, subtraction. I'll give you a couple examples and you can tell me if you want it done to your bank account. Okay? Okay, so addition and subtraction. These answers need to match the least number of decimal places in the measured numbers. Did you see the difference there? Addition, subtraction, least decimal places. Okay? Multiplication, division, least significant figures, right? Okay. Okay. I have I'm going to change your bank account by 0.01. So I'm going to subtract 0.01 off your bank account. Do you care? No, it's 1 penny, right? You lost 1 penny. And so that only had one sig fig, right? But the decimal place, it just gets rounded off in your head because you don't care about the 100th decimal place, do you? Okay, I'm going to multiply your bank account by 0.01. Oh, I just divided your bank account by 100, didn't I? You're going to be left with 1% of your bank account. You going to be happy with me? No, you are very angry. And so multiplying by a 1 sig fig number can have a huge difference, right? You're not going to round that off. You're not going to go, oh, that didn't matter. Big difference, right? Okay. And so you see that the decimal places in addition subtraction is what matter because you don't care about changing it by 100th, right? But multiplication and division, that matters a lot. If I divided your bank account by 0.01, you're going to be really happy with me, aren't you? Yeah. Okay. I got 2 more minutes. My goodness, let's get through this. Okay, so let's talk about, this is the rounding rules for numbers that your book gives. Again, it's what I had just mentioned. If you're ever rounding a large number with no decimal point, you substitute the zeros for numbers that are not significant. Be aware that you can sometimes end up with some weird edge cases where you take like a 2.1 divided or 2.2 divided by 1.1, and now all of a sudden you don't have any decimal place, right? Because it just happens to fit into each other. Okay? And so keep those sig figs in mind. If you don't have a sig fig that you already have something to write, it's a 0 you add to it. Okay, rounding each step, very important you don't do that. Scientific notations are very nice for scientists because they already have the sig fig kind of worked into them. And so they're represented by this. C is the coefficient, times 10, and then it's to a power. And that's how you represent how many zeros it would have behind it, okay, or in front. Now again, this right here, this n, this is the exponent. It's again telling you the tens place. If you have a positive exponent, this actual number is going to be greater than 1. So it's going to be times 10, times 100, times 1,000, right? You have positive exponents here. If you have a negative exponent, it's going to go the other way, right? And so we're going that we have a number that's going to be between 0 and 1. It's going to become lower and lower and lower as we get more and more negative there. In the scientific notation, only your significant figures can be shown in your coefficient. You don't have to write anything else. There is no need for placeholder zeros because you get to pick where that 0 would be, right? So you always just, all those placeholder zeros, we're moving up into here in scientific notation. It's very nice, very convenient. This right here is different scientific notations and their meanings. Is everybody okay with that so far? Okay. Okay. We'll leave off on there, starting on percents next time. You all have a great day. Have a wonderful week. Yeah, you get a long weekend. Lots of fun times with homeworks, right? Yes. Are they? Yeah. No, I'm a chemist. We're just used to work at this point. Yeah. Maybe it's all the drugs, right? Bye-bye. Mm-hmm. Uh-huh. Oh, okay. Do you want to? We can change it.